you need to pause, read, keep up. Here's the gist of it. You have a bullet that's initially moving at 540 meters per second. It's going to strike a stationary wooden block. The system is going to get embedded and then move across this rough segment, comes to a stop. And then it wants us to find A, B, and C. A, the amount of work done by friction. B, the mechanical energy lost during the collision. And C, the time it takes to travel this unknown distance, D. Okay. All right. But before you do that, I like to go ahead and make sure all my units correlate. Here, I notice that the mass of the bullet for this particular problem is given in 27 grams, but the mass of the wooden block is given as 2.8 kilograms. So that's gram versus kilogram. So I need to convert 27 grams to kilograms. So all my units are in kilograms. Okay. So to convert 27 grams to kilogram, times it by 1 kilogram and then divide that by 1,000 grams, because for every 1 kilogram it has 1,000 grams. All right, grams cancel out and then it'll leave you with 0.027 kilograms. So now that I have everything in kilograms, let's go ahead and crack it out. To do part A, how much work was done by friction, I need to focus my attention after the system has embedded itself and travel across this rough surface. That's because I know VF here is 0. And so the only thing I do need to find is the velocity after the system has been embedded. Okay. So I'm just going to set up work kinetic energy theorem. So I think this is the easiest way to find net work for this particular problem. Why? Because I can just use delta KE. I can break delta KE into KF minus KI. But if you are looking at just a rough segment here, KEF is going to be 0 because the problem sets that VF here is 0. Not only that, I think in the statement it says it comes to a stop. So I'm just going to cross that out. So the only thing I have left really is net work, which I'm trying to find is equal to KE or negative KEI here. So I'm just going to go ahead and carry the negative sign down. And then KEI can be broken up into 1/2 mv squared. But you notice here in my work, this is m bullet plus m wooden block because the system is now moving as a whole. It has the bullet is inside the block. So make sure you plug in MB plus MW here. And then VI square here. This is VI square. Even though it says VI, it's really this VF in the diagram. Okay. So the block was initially at rest and then it got struck and then it moves off with some velocity. But this velocity, which is the final velocity and momentum, is going to be your initial in the second segment. Okay, so while the subscripts are different, it's really the same quantity. All right, so let's go ahead and set up conservation of momentum. Why? Because the only thing I do need to find is VI here. I know what the mass of the bullet is. I know what the mass of the wind block is because those were given to me in the statement. So the only thing that's keeping me from finishing this is just the VI here. But once again, VI is really the VF for this collision segment. Okay, so I'm just gonna set up conservation of linear momentum. The initial momentum is only contributed to the bullet because the bullet was the only object moving. The wooden block was initially at rest, so it has no momentum. So I'm just gonna go ahead and expand this to the second statement. Mass of the bullet plus the initial speed of the bullet equals to the mass of the system. Because it is embedded, it will move together with some final velocity, and this once again is just VF like that. All right. To get VF by itself, divide both sides by the mass of the system, which is mass bullet plus mass wood. So that's what it looks like. And then really I know everything. I know the mass of the bullet, I know V bullet, and then I know the mass of both these objects that's in the denominator. So I'm just gonna do a little plug and chuck here. Mass of bullet is 0.027. Once again, I'm using 0.027 because I converted that to kilograms. And then the mass, the initial speed of the bullet is given in the statement as 540 meters per second. And then the mass of the whole entire system, which is 2.8 plus 0.027, which is 2.827. And plug and chuck on your calculator, you should get a final velocity of about 5.157. So this is the final velocity for momentum. But it is the initial speed heading into this rough segment. So I'm just going to go ahead and plug it in to VI here. So VI is just 5.157. We're going to square that. And then if you plug this on your calculator, you should get work of about 37.6 joules. And the answer is negative here because it says calculate the work done by friction. And friction is doing work against the object's motion. So therefore, there's a negative sign there. Okay, so that is the answer for part A. All right, let's crack out part B. Part B asks us to find how much energy is lost during the collision. So to do that, I need to know what the final velocity is after the collision, but we already just found that using this strategy here in part A. So really, I'm just going to go ahead and crack this out real quick. E loss is just KEF minus KEI, and then here KEF is just 1/2 M block plus M wood. Don't forget they move as one now, so make sure you add these masses together, and then VF squared minus 1/2. But KEI, the initial kinetic energy of the system, is only contributed by the mass of the bullet, right? Because initially the wooden block was not moving, so there is no KE for the wooden block. The only KE for the whole entire system comes from the bullet itself, because it was the only thing initially moving. So you notice here, while the first term KF here has MB plus MW, KEI though, the only mass here is just mass of the bullet. So make sure you differentiate as you practice. All right. Here, I'm just going to plug and check. Once again, we already found earlier, mass of the bullet plus mass of the wooden block is 2.827. And then the final velocity after the collision we calculated already is 5.157. Don't forget to square that. And then the mass of the bullet is given. The initial of this bullet is 540, which is also given. So if you plug in all these in the calculator, the first term is about 37.6. The second term is 3,936.6, and take the difference of that, you get a negative 3,899 joules. So there's about 3,899 joules of energy lost during the collision, and that is the answer for part B. So not too bad. All right, let's crack out part C. I'll show you different strategies to do part C here. Hopefully you keep up with the different strategies and pick one that fits your brain the most. Okay. Here's just calculate the time to travel the distance d. The distance d is not given to us in this particular problem, but we know that it travels some distance before it comes to a stop. So I want to focus my attention here in the second part of the diagram here, because this is where the rough segment is. Okay, to find time, there's a bunch of different ways, so in no particular order. So here we go. Impulse is defined as the change in momentum. Impulse is the force times the time of contact, which equals the change in momentum on the right side here. So to find delta t, I can divide both sides by f, but at the same time, I'm going to go ahead and break up delta p into pf minus pi, and then I divided both sides by f, so that's why the f is in the denominator on the right side. I want to cross out pf because if I'm just focusing on this right side of the diagram where the block moves into this rough segment, it says that vf is equal to 0. So it comes to a stop. And again, if it comes to a stop, there is no final momentum. So I'm just going to go ahead and expand pi, the initial momentum. The initial momentum for this right side is contributed by the mass of the bullet plus the mass of the block and vi. And then the force here is just the force of friction, because the only force acting on this segment is the force of kinetic friction along the surface. Okay. Now, we know that f of k, though, is mu k times f of n. I don't know what f of k is. It was not given to me. However, the coefficient of kinetic friction was given. So I can go ahead and break up f of k into mu k f of n, so that I can utilize the information given to me here, which is mu k. All right. However, as you can see, I highlighted my work here. I don't know what f of n is, but for this particular problem, pretty light work. So watch the diagram here. I'm just going to draw f of g for the whole entire system, which is mass of the bullet plus mass of the wooden block. F of g is going to point down the page. But for this one, at the same time, there's an f of n equal in magnitude, but opposite in direction. Okay, so there's only two forces in the vertical direction for this particular problem. So we can say Fn is equal to the magnitude of f of g. So I'm just going to go ahead and plug this in. Here, wherever mu k and f of n is, I'm just going to substitute out f of n. So f of n is just mg, or f of g. But at the same time, I can break up f of g into mass times gravity. But what mass? The mass of the bullet or the mass of the system. So anyways, it doesn't really matter. It's going to cancel out anyways, as you can see in my work here. Okay. So the only thing you do need is vi, mu k, and g. And therefore, if you plug it in, here, vi we already found from our previous work. Okay. After the collision, the bullet and block moves off with a speed of 5.157. So that's our initial entering this rough segment. Hence, the numerator is 5.157. And the bottom here is just 0.2 times 9.8. So once again, we're just looking at magnitude here. So don't plug in a negative 9.8 here, because if you plug in negative 9.8, you get a negative 10, which makes no sense. Okay. once again, f of n is equal to the magnitude of f of g. So here, f of n is pointing upwards, so the magnitude of g would just be a positive 9.8. All right. Anyways, if you did plug in a negative 9.8, just make sure that you use common sense. Time cannot be negative, so just leave the negative sign out. All right. So it would take about 2.63 seconds. Okay. All right. The other way to do it is to go ahead and just apply the average acceleration function, right? By your kinematics, average acceleration is change in velocity over change in time. So, but here we're asked to find time, so I'm just going to do a little switcheroo. I'm going to move delta t up to the top left and move a down to the bottom right. Or you can say multiply both sides by delta t, and then at the same time divide both sides by average acceleration. But I want to break up delta v into vf minus vi, but once again, vf is 0 because the system comes to a stop at the end of this rough segment. Vi I know already. I know vi is 5.157. The only thing I don't know is my average acceleration as it slides across. Okay, we know that it decelerates because it's moving and then it comes to a stop. So there is some sort of acceleration occurring. All right. So you notice here, I just went ahead and plug in my VI. I know my VI is 5.157. The negative signs I just carried down my work. So the only thing I don't know is the average acceleration, which I highlight in yellow there. So I'm just going to set up Newton's second law to find A. Okay. Well, net force is equal to ma, but the only force horizontally in this particular problem is the force of kinetic friction. What mass? The mass of this entire system, because it moves together across this rough segment, and there's acceleration. So make sure you plug in the right mass here. If you don't plug in the right mass, you might mess up with yourself later. Okay. Here, the only thing I do need to find is a. So to get a by itself, I'm just going to go ahead and divide both sides by the sum of mb plus mw here. So I'm going to go ahead and plug it in. Fn is equal to f of g once again, and then break it up, and then as you can see, fg is just mass times gravity, but mass of the system, and then that mass of the system is going to cancel with the mass of the system on the right. So the acceleration for this particular problem is just mu k times g, which hopefully you know from the previous video. Okay, but don't assume this is all the time. This only works. This statement is only valid when the only force acting on the system is the force of kinetic friction. So don't just take the statement and run with it for other problems, because then you get the wrong answer. All right. So we know mu k is 0.2. We know g here is negative 9.8, and then we simplify that. We know the acceleration is negative 1.96, which makes sense, right? The velocity is moving to the right, but the system is slowing down, which imply that a has to be negative because it's acting against the system's motion. All right, so here a is negative 1.96, and I'm just going to plug and check. So here I'm just going to go ahead and substitute in for a average. If you plug it in your calculator, negative 5.157 divided by negative 1.96, you'll get the same answer, which is 2.63. As you can see, it doesn't really matter which strategy you utilize; it's all the same. Okay. The last method, if you like, is just use the average velocity functions. I can use it because a is constant. The only force acting on this in the horizontal direction is f of k, and f of k is a constant. Therefore, a is a constant, which means I can use these kinematics equation. So average velocity by definition is delta x over delta t. Equals vf plus vi divided by 2. But once again, vf here is 0 because the system comes to a stop at the end. I know vi being 5.157. The only thing I don't know is delta x, so I'm just going to go ahead and flip the function upside down to get delta t up in the numerator, because that's where I have to find. So therefore, to get delta t by itself, I'm just going to move this delta x up to the right, or multiply both sides by delta x, however you want to say it. Okay. So delta t is equal to 2 times delta x divided by vi. Here I highlighted delta x because I don't know what delta x is. I know what vi is already. So the only thing holding me back in this strategy is how far did it travel. Well, that's okay. Well, if you just use a little bit of knowledge or common sense here, we know that the work on the system during the segment is just the force of friction times its displacement. But we already found the work done, right? Earlier, we found the work, I think, in part A, which is negative 37.6 joules. Here, we can just use that information. We know f of k is mu k times f of n, and the delta x just gets carried down. So I can just break it up, right? Mu k is just 0.2. F of n is just m times g, right? Same skill here. If you look at the diagram that I set up for you, f of g is f of n is f of g, at least the magnitude. So here, instead of f of n, I just did f of g. but f of g is just mass, which is the mass of the whole entire system here, times g. So the only thing I don't know here is my delta x, which is what I need up here. So I'm just going to clean this up a little bit. Right? If you plug in 0.2 times 2.827 times negative 9.8, you'll get a negative 5.54. And then to get x by itself, divide both sides by negative 5.54. So the negative signs will cancel out. So that'll just leave us with 37.6 divided by 5.54. And then that cleans it up to be about 6.79. So I'm just going to plug it back in for delta x here. And if you plug it in and do a little calculator work here, 2 times 6.79 and divided by VI. Once again, we already calculated this is the after the collision. It moves off with the speed of 5.157, and you get the same answer, which is 2.63. Whichever strategies you like, it should always work out. Okay, I hope that helps. Pick one. Stay nerdy, don't be whack.